Hi, everybody. It's Mrs. Gladfelder here. Just a lesson here on something called the ideal gas law. That's what we're going to be taking a look at today. In the ideal gas law, and I guess I didn't get, there we go. In the ideal gas law, we allow all four of the variables that you can measure about a gas to be able to change. I know that you did Boyle's law, which involved pressure and volume changes. That was when, the moles and the temperature were constant. You did Charles' law with volume and temperature changes when the pressure and the moles were constant. You did Amonton's or Gay-Lussac's law. Gay-Lussac's law, that varies which name that goes by, which is how the pressure changes with the temperature if the volume and the moles are constant. But what if all of these are changing at the same time? So we're going to develop that ideal gas law here and also show you how you can rearrange it to find the molar mass and or the density of a gas. So you kind of established some things that the pressure would be directly proportional. Gosh, I gotta hate when that happens, but it happens. But pressure is directly proportional to the inverse of volume. You guys know from your algebra classes, hopefully, that if you have a direct proportion that goes through the origin, you can write an equation for that line. So on the y-axis, we have the pressure. So I'm putting P in for the y. M is the slope. The slope of that line will stay constant as long as temperature and moles are constant. So we're just going to write the word slope in here. We don't really need to know what it is. We just need to know that it is, for some reason I keep pulling that up. We need to know that it is, the same. And then on the x-axis, we have the inverse of volume. So put that in for x. And then we don't have to include the intercept because, of course, it should go through the origin. We also did that Gay-Lussac's law, that if you graph pressure and temperature, it'll be a direct proportion as long as that temperature, remember, is in kelvins. So pressure is going to be equal to, let's see if I can write the word slope this time without, must be something going before. And that slope will stay the same as long as the volume in the moles are constant. And then on the x-axis, we have temperature in Kelvin. And the other variable, which we held constant in Boyle's law, Charles' law, like all those laws that you already did, the amount of gas was always held constant. Well, if we let N be the moles of gas, or like how many particles of gas, if we have a container of set volume at a set temperature, as you increase the number of moles, then there's more collisions with the walls of the container, and so the pressure will increase in a direct proportion to how many particles are, in there. So again, we can write an equation. Pressure is equal to the slope times N. So what they do in the combined gas law is, well, or not the combined gas law, I'm sorry, the ideal gas law is what if nothing's held constant? And they kind of just put all of these together and make one graph where you have the pressure on the y-axis, and on the x-axis you have the moles times the temperature over the V, because pressure is directly proportional to moles, directly proportional to temperature, but inversely proportional to volume. And what they found is that they got a graph and they got the exact same slope every time. They got a universal constant slope. Didn't matter what gas. It didn't matter which one of these variables you changed, the other ones would adjust in response to it. And they always had the same slope, so they used the letter R for the slope. Okay, now let's write an equation for that line. On the y-axis, we have P, and we have the slope. They use the letter R, which is the universal gas constant because it works for all gases in all situations. And then we have NT over V. To make it a little simplified, they cross multiplied and said PV, and then they rearranged these nRT. And this equation right here is known as the ideal gas law. And sometimes it is also called the equation of state because it can describe the state of any gas. To use this equation, it depends what units are used for R. Whatever units are used to determine your R value, those units have to be used then for your other variables. You can look up different R values on the internet, but I think the easiest thing to do is to use pressure in atmospheres, volume in liters, of course, N stands for moles. And when you do that, and the temperature is in Kelvin, then this is the value of R, 0.082057. You can check that. You guys remember Avogadro said that 1 mole of gas is 22.4 liters at STP, which would be 1 atmosphere and 273 Kelvin. So you could solve for R using 1 mole, 22.4 liters, 1 atmosphere, and 273 Kelvin, and you're going to get the 0.082057. So that is known as the universal gas constant. It works for every gas. So we're going to use that. So I already kind of went over that, but went over that on the last slide. That, if you could get the value of R by plugging those things in. Remember, R would be equal to pressure times volume over NT. And so if you plug those in, you would have liters times atmospheres over mole, the value of R. All right, so one thing that we're supposed to note in honors chem, but we really don't have you do much in the way of calculations at all with this. You would do this if you take AP Chem or future college chemistry classes, is that this is called the ideal gas law because there are some conditions where ideal gas behavior kind of breaks down. Some of those conditions would be like if they're in a really low volume at a high pressure, then the particles are really close together. And if they're close together, they're usually nonpolar substances or not that polar. And with the great distance between particles, they don't usually attract each other. But if you put them in a low volume at a really high pressure, they can start to attract each other a little bit. In the low volume, the space that the molecule itself takes up does start to kind of affect the overall volume of the gas. And if they're at really low temperature, they're not moving very fast. Now, a lot of substances under these conditions are going to turn into a liquid. But there are some things like, helium or neon or just other gases that you can get them at a really high pressure, low volume, low temperature, and they'll still be a gas, but what happens is this equation does not accurately then, it's pretty close, but it doesn't accurately predict their exact pressure, volume, moles, and temperature in relationship to one another. So there is an equation that is used to account for that, but we aren't going to do those calculations right now. What I want you to know is that under typical conditions, this equation works for all gases in all situations. But if you have extreme conditions, then the equation can break down. Okay, so, all right. So here's some sample problems. Let's just do a sample problem together. Okay. So I usually like to try to, list out what do I know. We know R, it's always the same number. So 1.35 grams of nitrogen, I'll take that and convert that to moles. Remember, you've got to double the nitrogen. It's 28.02 because it is diatomic. And so I got for the moles, I got 4.82 times 10 to the negative 2 moles of nitrogen. So whatever gas you have, you can always put it into moles. I've got the volume, 1.25 liters. I've got the pressure, 115 kilopascals. I need to divide by 101.325 to get that into atmospheres. And I got 1.13 atmospheres. And you can see then that what I'm trying to find is the temperature. Okay, so you can take your equation and solve for the temperature. PV equals nRT. To solve for temperature, we got to divide both sides by nR. So the temperature is going to be equal to PV over nR. And really from there, you just take your numbers from above and plug it in. We've got the pressure, we've got the volume, which was already in liters for us, so that was nice and easy. On the bottom, we got the moles. And then the value of R, 0.082057 liter atmosphere per mole K. And always remember to go through and like your atmospheres divide out, your liters divide out, your moles divide out. Got no units left on the top. On the bottom, we have 1 over Kelvin. Well, that's going to give you an answer in Kelvin. So 1.13 times 1.25, divide by the value of R, and divide by the number of, oh, and I had a miscopy there. Did you all see that? You might have. That happens to me sometimes. Apologize. This is supposed to be a -10. And I got 357, which is in Kelvin. It says report the answer in Celsius. Watch out for those kinds of things on WebAssign. And so to convert this back to Celsius, we have to subtract the 273, and I got 84 degrees Celsius for my answer. Okay. So you can take a look at this problem and start to list what you know. And you can pause here and try the problem on a piece of paper. That would be ideal. And then, restart it because I'm going to show you how to solve it. If you are totally lost, you are welcome to just follow along here, but you might want to try it on your own first. So I see the volume as I'm reading. I see the pressure, which needs to be converted into atmospheres, 8.64. The temperature, 77 is Fahrenheit. I don't need that. I need Kelvin, so I'm going to take the 25 and convert that to Kelvin, which is 298 Kelvin. And what I'm looking for here is the moles, which I can then eventually convert into mass. So if I'm looking for moles, okay. So if I'm looking for the moles, I got to divide by RT this time. So the moles are equal to PV over RT. 8.64 atmospheres, 5.0 liters, R 0.082057, and the temperature 298 Kelvin. So again, you can get rid of, your units, and you're going to end up with moles. So I need to plug this in, 8.64. And I got 1.766554. Big long number. I would keep the extra digits. You're going to get the moles right there, especially if you're doing WebAssign. This is going to like if you round off here and then round off again, it's going to change it. But remember then to convert your moles into mass, we need the molar mass of the propane, which is 44.11. So 44.11 grams in a mole of the propane. And so you want to take the moles that you got and you want to multiply by that number. And hold on. And I got 77.9, which now I am going to round off to 2 sig figs. I would just say 78 grams of propane in that tank. Okay. So whatever number you get for the moles, you just convert it using the molar mass. So you're going to see a variety of problems on WebAssign. So then it says you're also going to find problems on WebAssign that ask you about the molar mass and the density. So for this, what I want to suggest is that if you look back, remember, how do we get the moles of gas right here? Remember, we take the mass of the sample and we convert it by dividing by the molar mass. You know, how many grams are in a mole. So what we can do is substitute in for right here, we can do the mass of the sample over the molar mass of the sample, okay? And so we can then have PV is equal to mass of the sample, not the molar mass. This one's the molar mass times RT. You can rearrange that then to find a density. Density is mass divided by volume. So I'm going to divide both sides by volume. Okay, and that'll get rid of it over here. Now I've got mass over volume. I want to get the mass over volume by itself. So my next moves are going to be divide by RT. So it needs to be on the bottom. And multiply by the molar mass. If I multiply by the molar mass, then I get rid of everything on the right side except the mass over the volume, which is density, right? And on the other side, I have pressure times the molar mass over RT. So you might want to use this equation when you're doing the WebAssigns. There are some where they give you like the mass and the volume and they're looking for the molar mass. There are others where you're looking for the density and you don't know the mass or the volume. So you have to like add up the molar mass of the gas. So that would be, you know, something that a variation. So since this is one with density and molar mass, our equation, we need pressure, we need molar mass. You know what? I want to use a different, hard to see, so I apologize. Let me go back to something then. So if we're going to use that equation, we need pressure and molar mass. R we know. We've got temperature and density. So in this one, as I start reading, I've got my density in grams per liter. It has to be per liter because PV equals nRT, the R value, liters is the unit. 25 Celsius, I have to make that into kelvins since they have the 10th here. I will keep a 10th. And so make it like that. And the pressure is already in atmospheres. And so you can see here the molar mass is the only thing I need to find. So pressure, molar mass over RT equals density. If I'm trying to solve for the molar mass, I got to get rid of everything else. So I'm going to multiply by RT and divide by P. I almost like how the highlighter writes better than the pen. You can see the pressure will divide out, RT divides out. And so the molar mass is going to be equal to RT over, oops, see, I missed the D. Look how easy that is to do. So dRT over P. So I need the density, R, temperature, all over the pressure. So looking at my units and what divides out, the liters, the Kelvin, and the atmospheres, and I'm left with grams over mole. So I am left with grams per mole as my answer. Okay, so that is a molar mass. That works out. Your unit should always give you something that makes sense. So I was starting to type on my calculator and made an error. So you can multiply everything on the top and divide by the bottom. And let me see, how many sig figs do we want? 3. So I got 25.4. So whatever this gas is, that is its molar mass. So this is actually a strategy that can be used to identify a gas. Like if you know the volume of a tank, you can fill it with a gas, weigh it again, and see what the gas weighs. Use the volume and the mass to get the density. And if you can measure the pressure in the tank and you know the temperature that day, you can plug all that in and find the molar mass of a gas. We actually used to do that a lot in the research that I did in college. So hopefully you've seen, how to just use the ideal gas law itself, PV equals nRT, and then how you can rearrange it to do molar mass or density calculations. And good luck with WebAssign and giving your answers with correct sig figs and labels.